reactions with this acyl chloride and see how we can turn it into some of these carboxylic acid derivatives on the left side here, going down. So just to refresh, we saw that the acyl chloride is the most reactive of all the carboxylic acid derivatives that we have here in the list. And we came up with an explanation for that based on resonance or lack of resonance and the leaving group ability. Okay, then we made it. So now, as I mentioned here, so note the similar mechanisms that we're going to see with these different reactions. And there's going to be a few different things that come in here and there. As a starting point, let's consider this hydrolysis reaction. So we're going to react our acyl chloride with water. So we have a generic acyl chloride here. We're going to react this with water, and you end up forming a carboxylic acid and HCl. This is not a useful reaction really at all, except to use it to show the mechanism. And so we've already kind of seen something like this. Let's have our acyl chloride and water. And you'll notice water is a weak nucleophile. When we were reacting water with aldehydes and ketones here, with our weak nucleophile, we would usually have to protonate the carbonyl group. However, because this is such a reactive species, the chloride is just pulling electron density away. It's not really donating electron density through resonance. It's just pulling it through induction. That makes this carbon very electrophilic, as is, so that our weak nucleophile can go ahead and attack without protonation. So we're going to end up having an intermediate like this. And let's go ahead and just kick out the chloride here. We're reforming our carbonyl group. And we're going to end up with have this, which we're going to form HCl. So that gives us a carboxylic acid and HCl as our products that we've seen. Not a useful reaction, but other than to show the mechanism. Now, as I scribbled up here, is that a lot of times you're worried about this reaction actually happening because you want to preserve your acyl chloride. And forming HCl can actually cause some problems. If you have a compound that has something that's sensitive to acid, you're forming a strong acid. So a lot of times, pyridine is added. So this is pyridine. And what this will end up doing is it's going to react with the HCl. So let's put this down below here. So pyridine with HCl is going to react in an acid-base reaction. Oops, good job. Okay, I don't know, can everyone hear the leaf blower in the background? It's getting closer. It's like they're walking away. Okay. Yes. Okay. So Lorianne asks why the oxygen from the carbonyl group doesn't grab the hydrogen. So up in this original step, perhaps here, with this acyl chloride being very, very reactive, we don't have to have acid in our reaction. Actually, we generate acid, which we have to deal with later on. But because this chloro is pulling electron density away, it makes this carbon then very electrophilic. So the oxygen and the chlorine both pulling electron density away, so that even a weak nucleophile like water can attack, so that we don't have to actually protonate this group. We're going to see later on with other carboxylic acid derivatives that we actually do have to protonate that group. Okay, excellent. Okay, so hopefully if you hear the leaf blower, they're walking away. I thought we were supposed to be able to access the building today from the email we received, but when I went there's all these signs on the door saying no one can enter today. So anyways, hopefully tomorrow will be fine. Okay, so now let's look at a similar reaction, and we'll see that let's use methanol now as our nucleophile in the presence of pyridine and with an acid chloride. And this is going to be the same thing as what we saw with water. Rather than HOH, it'll be CH3OH. I think my pencil is, make it one size bigger. Let's try this again. It's a little better. So I have methanol. We do not have to protonate this.